Right, good afternoon, everyone. So yesterday's drama with the connection with my laptop resulted in something good, and that was that Simon immediately ordered an HDMI to VGA adapter, which is now working quite successfully. Sorry for those of you who have already been to the ASSP summer school, you would have seen this lecture already. If you could head over to github.com/Stéfan V/teaching, you'll find an archive with a whole bunch of tutorials in it. And the one we're going to be looking at today is 2013 ASSP Zurich Cython. So that's the Cython lecture presented at the last Advanced Summer School in Python. So you could clone the whole repository, but it might be a bit big. Maybe you could just download the files as you need them. Have you all got the address? If you've copied the address, then I can navigate away. All right. Right, so I'm sure many of you have run into the problem that Python isn't exactly the fastest language on the planet, especially when it comes to executing for loops. The situation is surprisingly often not as bad as you might realize, because for loops aren't as evil as many people make them out to be. In fact, sometimes for loops are quite advantageous. If you've got an operation that requires a lot of memory to execute, then breaking that operation up into smaller parts using a for loop to iterate over smaller parts of your array and doing the computations over those smaller parts can often result in a speed up, because you can use the caching of the computer better. You don't overload your resources as much. But at the same time, yes, there is a cost to executing loops in Python. So this chart is just to give you a rough indication of the relative lie of the land. We've got our low-level languages, things like C++, Fortran, and then higher-level languages like Python and Julia and these kinds of things. Of course, nowadays we've got a very interesting middle part of the landscape with languages like Julia that can use LLVM to compile straight down to a low-level language. And you can do the same thing using Numpy for Python nowadays. But Cython is a solution that tries to do something different. It also tries to bridge that gap between a language that is easy to understand but a little bit slow, trying to bring it down to a language that is more difficult for a human to write down, but that a computer can generate fairly successfully and then can execute a lot more quickly. So how do you get from Python to C code? Well, that's why we use Cython. So Cython takes a piece of Python code and it compiles it into C. That C you can then compile into a shared library that you can pull back into Python. Now, it's hard to do. I mean, Python is a very dynamic language. It's not always clear exactly what type, for example, the user has in mind when he's writing an expression, when he or she is writing an expression. So you have to give the computer some hints in order for it to do that. So I'll show you how to annotate your Python source code in order to make it make Cython able to do that. You'll see I wrote T break in here. I've noticed that an experiment that takes 2 minutes to run, I will sit and wait for it in front of the computer. The moment that experiment takes 4 minutes to run, I get up take a break, go make some tea. So for me, the moment problems start taking too long, I tend to drift away. So often for me, there's a huge jump in productivity if I could just get my problems to run in sort of in that bit of time that will make me sit there and keep paying attention. All right, so like I say here, Cython allows us to cross that gap that I was just talking about. It's great because we can keep coding in Python, which is a language that allows us to express naturally, it's close to what we're thinking, and it's almost writing down English there. But you still have the speed advantage of C. Can you have both these worlds combined? Yes, certainly. You can. Wow, what was that? So what kind of speed ups can you expect? Well, we're looking at, if you just take your plain Python code and you compile it down, you're looking at a 2 to 8 times speed increase. But if you add annotations, so if you help Cython along a little bit by telling it more about your code, then you can typically get 80 or 100 times speed improvement. So yesterday we saw a very nice tutorial on profiling, and that would always be my first recommendation. Don't optimize your code unless you have to. Go and run the profiler, see where things are slow. I've seen so many people spend hours and days optimizing a piece of code only to find out later on that they could just have found a better algorithm. If you can go from an order 3 algorithm to an order 2 algorithm, it makes no sense to try and optimize the order 3 algorithm. So these are some use cases. You can optimize existing Python code. You can wrap your C and C++ code. I'll show you how to do that. You can break out of the global interpreter lock. So you can have threading, essentially, which you can't very easily in standard Python. And then you can mix C and Python, but without the pain of coding in the C API. How many of you have coded in the Python C API before? You're not in an institution, you're here. That's good, but unusual. A lot of people don't enjoy that experience very much. Right, so here's what we can look at today. You can guide me in the direction where you want to go. If you want to see one aspect of this more than any other, let me know. But we can take, first I'll just take a piece of pure Python code and I'll benchmark it. We'll see which part is too slow, then we'll run the code through Cython, compile it, benchmark it again, and then finally we'll annotate the types and benchmark again, and we'll see what is the speed improvement that we get at each stage. So we expect it to be faster at each stage as we go along. Then I'll show you how do you integrate Numpy arrays with Cython, how do you use multiple threads, and then how do you wrap C libraries. The example problem I'm going to use is a simple integrator. So I'm going to take a function, I'm going to sample that function at different points, and I'm going to approximate the integral as the area underneath these blue bars. So we'd simply take the function value, we draw a block underneath it, and of course the more blocks we can fit in underneath the function, the more accurate our integral approximation becomes. What is worth noting here, I've got 1, 2, 3, 4 blocks in this example. So dx, the width of each block, becomes my total interval, which is 2 in this case, divided by 4. So it's a half. So the idea is then that we would head for something like this and keep increasing the number of blocks and then get a good approximation to that integral. All right, so there's the pure Python code. So the first line is just to make sure that we use proper floating point division. Otherwise, Python 2 gives you integer division. So you see that if you do 1 divided by 2, you get 0, instead of a half. Then we define our function that we want to integrate. In this case, it's x to the power of 4 minus 3 times x. We're going to define an integration function. It takes two parameters, a and b as an input. That's the interval over which we would like to integrate. And we're going to use n blocks. So we're going to subdivide that segment into n blocks. As I just told you, the width of each block, dx. Can you guys at the back read this? Is that right? OK, so dx, the width of the block, is equal to the interval divided by, or the size of the interval divided by n, the number of blocks. I start my summation with s equal to 0, and then for each block, I add the function value at that block position to s, and finally, I multiply s with dx. If this looks a bit confusing, I just factored out the dx here. I could have put it in there as well. So you would have had s is equal to dx times the function value, which is just that area underneath the block. Okay, so is it roughly clear what I'm doing here? Great. So, well, let's just see how fast that thing runs. All right, so I think that's, yeah. From integrate, we'll import integrate f, just to show you what's inside integrate.py. It's exactly what you just saw on the screen. So I've integrated that as integrate f, and then I use the built-in timeit function of IPython to run the function multiple times and get the minimum execution time. So I'll do integrate f over the interval 0 to 1. Let's say we take 10,000 blocks. OK, so 5.5 milliseconds. So what we're going to do now is we're going to take that Python file and we're going to run Cython on it. That will generate a .c file for us. Later on, I'll show you a little bit about annotation. We can skip that for now. OK, so then we've got the C file, and we compile the C file to a module. So let's do that quickly. Do that in a different tab. OK, so here I've got a setup.py file. I'll show you that file later on again. But you've just got a couple of imports that you need to do to get hold of Cython's build extension. And then you need to tell it to use Cython's build extension to compile your files. Here I've added all the extensions for all the different versions that I'm going to write now. But the first one I'm looking at is just integrate.py, the pure Python version. And I'm going to compile it into a module called integrate compiled. OK, so you run Python setup.py build ext -i that builds the extension in place, so in the current directory. And there it goes. So there you should now see an integrate compiled.so file. On Windows, you'll see a DLL. On Mac, you'll probably see a .dylib. And inside of that thing, well, it's just a shared library. So you see it's a binary file on the inside. All right, so let's pull that into Numpy, into IPython. So from integrate compiled, import integrate f compiled. No. Integrate f as what? Integrate f as integrate f compiled. There we go. All right, so let's time that one. So there's the original, and there's the compiled version. All right, so we've gone from 5.46 to 3.79, so that's about a 1.5 times speed improvement. Yeah, that's all right. We didn't do any work for it, so it's all for free. But I promised something much better than 1.5. So what can we do to improve the situation? Well, we can give Cython some clues, because currently it doesn't know very much about our code at all. It does have a basic type inferencing engine, but it's extremely conservative. It doesn't want to break your code. So here's what we can do. We will now change the .py file into a .pyx file, just to distinguish between pure Python and Cython code. And then we're going to annotate the code with the following. First, in our function f, we're going to tell it that the variable x is a double, or float 64 if you will. Then we're going to do the same for a and b, the beginning and ending of our interval, and then n, the number of boxes that we have, we're saying that's an integer. Then in C, we're defining the following. We're saying S is now a double as well. That's our summation. DX is a double as well. And I is a Python size type. I could just have written int here. It would have been fine. This is basically just an integer. Yeah?
And what range n? What happens there? What happens there?
What's that?
Range n. You take I from range n, right? Range n.
Yeah.
It's not a list anymore?
So range n will still be a list, but n itself is an integer that's specified right up here. But
so you wouldn't prefer to do something like x range n?
Oh well, this is now going to be compiled into C source code. So I'll show you just now. Once we've compiled it to C, we can have a look at exactly the expression that's being generated here. Yeah.
So since when is the cdef colon available in Cython?
I'm not sure. They did add this after a while. I'm not sure when that became available. But it's just a more condensed way of writing.
It's very nice.
Yeah.
It's very old, like from 0, 1 something.
Oh, is it? Yeah, it wasn't there since the very beginning. You had to write cdef in front of everything before. All right, so all we did is we added some types to our code. It's the only thing we did. And the question is, will this improve the speed of the generated Cython code significantly? Well, let's see. So this version, I think, is called integrate types. So let's import that one. And here's our previous compiled version. And here's the one with the types annotated. (1.7 milliseconds per loop). So 3.8 over 1.7, that's another 2.2 times speed increase, above the 1.5 that we've had already. So we're now at 3 and something already. All right, so that's looking better, but still a far shot from what I promised. So why is it still so very slow? Well, here's the problem. So you're executing this for loop, and inside the for loop, you're calling the function f. But f is a function that is defined in Python. So here's how it's executing. You call integrate f. It now goes into the C layer, and your for loop is now existing in the C part of the code. But the for loop keeps calling out to a Python function, and then the answer is returned back into C, and the for loop iterates. But this means that the slow Python code, which is very expensive to execute, this is being called time and time again. So we would like to avoid this situation if possible. And the way we can do that is by telling Cython, let's redefine that Python function f inside pure C. So that's how we do it. We simply put a C def instead of a def, and then tell it what is the return type going to be. The function is going to return a double. And just to make it a little bit fast, I also unroll the x to the power of 4. Because if you call x to the power of 4, in the C code, it's going to call the power function. And x times x times x times x is actually faster than the power function. Then I also tell it to use, right at the top, you see I tell it to use C division equal true. That means don't be careful when you do division and catch floating point errors and that kind of thing, because Python's division is quite safe. It will always raise an error if you try and divide by 0, right? So we tell it, you just use the built-in division in C. Which, do I actually use that anywhere?
Divide by n?
Oh yeah, I just do it once. Okay, that's not even necessary in this example. All right, so that version is called Integrate Sci, I believe. Yeah. So it's imported from Integrate Sci. And timing it. There's the type annotated version that I showed you previously. It should execute in something like 1.7 milliseconds. Yeah. And then here's the Cython version, fully Cythonized. 67.2 microseconds. So 1.69 milli divided by 67.2 micro. That gives us a nice 25 times increase. But we should actually compare against our original Python, which was this guy. There we go. 81.25 time increase in execution speed. Right. So that's what Cython's all about.
Sorry?
Yeah.
How would Numpy stand in this?
What's that?
How would Numpy stand in this game? Like if you don't use a for loop, but
If you did the same thing in Numpy, it's in SciPy, right? I don't know how it's implemented. Which one do we use? Simpson or? What's the closest to the one that I implemented? TrapZ. Okay, and it takes as input okay, y, dx, and so if I were to write an equivalent function, it would look something like this. And
Probably the other way around. B minus A.
All right, and then we need we first need our y. So that would be and what is it to the power of 4 minus 3 times
RT quad is better suited.
what's that? Quad.
Integrate quad is
What's its signature? Is it the same?
function AB. The name of the function.
Or does it take a function as input?
Yes.
Okay, let me first try traps because I now know the signature of that one. So it takes the y values, which would be x to the power of 4 minus 3 times x. It takes my dx. That's it. Okay, let's. Can you see what I did wrong?
Specify the start and end conditions.
Ah,
Sorry. My mistake.
so y and x can be none, but it must be no. It must. That seems fine. There's my. There I've got
Dx equal to dx.
dx equal. Thank you. Yes, that would be it. There we go. Yeah, okay, so that's good. So it's about 14 times faster than the traps in SciPy. But I mean, the idea is not that if you can do it in Numpy, of course you're going to do it in Numpy. And if the factor is maybe 2 and it doesn't really matter in your code, sure, stick. I mean, don't go into Cython unless it's absolutely necessary. So someone asked me a little bit earlier, how would the code look? So Cython's got this useful feature. You type Cython -a for annotate, and let's run it on our final version. So it generates, and I think I also want to run it over the types one. So you'll see it generates HTML files for you. And if you open up those HTML files, you see something like this. So there's one of the earlier versions. And you'll see that the lines are colored in different depths of yellow. So that tells you how many lines of C code got generated underneath the hood for that specific line of Cython. And it's a remarkably good indication usually of how well you optimize your code. So if you see yellow, you normally want to pay more attention to it. So for example, we've got here this line, which calculates the bin width. If you double click on it, you'll see that there's like a whole bunch of things happening here underneath the hood. And that's because we are not using C division, but Python division. If you look over here, you'll see there's the function definition. Show you the type annotate the original one. So this is without any type annotation. And then you see that all the operations, you'll notice things here like pi number this, pi number that. So what's happening underneath the hood is each object, instead of being a C type, it's now an object in Python, and you have to use the Python API to manipulate those objects. So that's why you have calls to pi object this, pi tuple that, pi number that, and those things are slow at the end of the day. Whereas if you look at the version that we ultimately generated, it's mostly white. And if you look at this line of code, the variable names are a bit obscure, but it's just, it's machine generated. But you can see here is a variable s plus a function call to, a plus I times dx. So it's straightforward translation of what you see in the code above. And if you go into the function itself, well, there's a lot of code just to generate the function header and so forth. But once you get to what's actually being generated, can we find that? We should see something multiplied by itself 4 times. There it is. Sorry, this is actually the header of the next function that you see. There's the full extent of that piece of code. And you see there's an x times x times x times x minus 3 times x. Okay. But this is the kind of code that you would have had to write yourself if Cython weren't around to help. Hopefully with better variable names.
So could I ask a practical question?
Sure.
We've already put some effort, not very much admittedly, but some effort into translating that to Cython.
Yeah.
How much do you reckon that would have, why wouldn't I have just written the entire thing in C? It's a fairly straightforward thing, and then you can wrap it up with swig or something like that.
Yeah, so this is a... So this is a carefully chosen example to be easy to understand. But what happens when in your C code you suddenly want access to a Python function, or if you want to access attributes of a Python object and so forth? It's very difficult to blend C and Python effortlessly, whereas Cython gives you that entirely for free. And then you can still code on a high level, which you can't do in C. So of course you can write as much as you can in a little C-contained library and wrap all of that in Cython and bring it back. But just practically speaking, I would go crazy if I had to write half of scikit image in C, whereas doing it in Cython is fairly easy. All right, so this is just an example of how you can do that integrate function if you wanted to pass in an arbitrary function. Unfortunately, I don't know, maybe the situation has changed in the meantime, but I think the easiest way to do it currently is to generate a class and to have a member of that class that contains the function that you want to call, and then to pass in that class and call the class.f. Yeah, but I don't know of another way to do callbacks inside of Cython. All right, so how do we get hold of Numpy arrays? So here you see the syntax for C defining the array. We've got a function foo that takes as input parameter a two-dimensional array, and you'll see I say it's an array of doubles. And then I've got a square bracket with colon, comma, colon. In this case, I've got colon, comma, double colon 1. But that last colon 1 simply means that that is the dimension that's got a stride of 1. So that's our fastest changing dimension. So that would be your typical array where your columns are the ones that progress most quickly in memory. But if you don't want to specify that, that's fine too. You could just use square bracket, colon, comma, colon to indicate that you've got a two-dimensional array. The way it is here, Cython will complain if you pass in a Fortran ordered array. Right, so then you can create your output. Oh, there's something missing there. The word out is missing there just before the equal sign. So my output is defined as an array of double as well. It's the output of np.zeros like. So that answers your question a little bit. Like you wouldn't have access to zeros like, for example, in pure C. So you can call straight into that, and the output is assigned to a variable. And like I say, there's an out missing there. I needed the variable name there. Then I've got two variables, I and j. I run over the first dimension, the rows. I run over the second dimension, the columns. And then at each position, ij, I assign some value into the array.
If we don't know the array size, if we know it's a Numpy array, but we don't know the shape.
Yeah, so I actually query the array for its size. So I ask array.shape 0. So I get
dimensions actually.
Oh, if you don't know the number of dimensions, that's harder. Yeah, then you might have to write an iterator. I'm not sure. Yeah, that would be more complicated for sure.
In terms of declaring the dimensions of the array like you do in the argument. So you can write.
Yeah, I mean, you can always get in Cython, you can always get a pointer to a block of memory. So if you just want to manipulate a bunch of bytes, you can do that for sure. But then you must know how many elements to process because you can't run outside of that block of memory. So in some way you need to indicate,
Something.
yeah. I'll have to think a bit about whether you can pass arbitrary sized arrays like that. I don't think they allow it. Does anyone here know?
Or you can reshape it.
Yeah, so I guess you can always allow a one-dimensional array as input, but then Cython will complain if you pass in a two-dimensional array. So you might have to have a wrapper around it that takes the input, makes it one-dimensional, and then passes it into your C function.
You can accept anything and do an NumPy ravel.
That's right. Yeah. So you can you don't have to specify the type there at the top. You can just take away that double specification. Just have array over there, and then your first call inside your function, you make it array.ravel, which will pull it out into a one-dimensional array, and then you define a new type there for a one-dimensional array, and you assign it, and then you can work with it. Yeah.
You can even do an NumPy as contiguous array and enforce the type.
Yeah.
That will create a view on the object and do the cast if needed.
Yeah.
I have a question about you declare the memory view for the NumPy zeros like, and then you re-export the output. You recast it as a NumPy array.
Yeah.
NumPy as array.
Uh-huh.
Would it be in this case easier to declare directly a NumPy array in the CDEF instead of the memory view?
You can. He's asking that syntax that I described there that creates something called a memory view in Cython, and then you have to convert it back to a NumPy array here. There used to be a way in Cython for actually defining NumPy arrays in there, but the syntax is a little bit kludgy, and I think this is the more modern way of doing it. Yeah.
Another question. You mentioned that if it's yellow, it's probably something wrong with your code.
What's that? If?
You mentioned when you run Cython-A,
Yes.
if it's yellow, you probably need to optimize it.
Yes.
I just run Cython-A on this file, and it's like half yellow.
Mm-hmm.
So
Yeah, so it depends a little bit. Like the function definitions will always be yellow, but it's more inside your for loops that you want to make sure that the annotated file is white, because that's where the most of the time is going to be spent anyway. And you want to make sure that's a pure loop. Yeah.
Access to memory view tends to be more yellow. So if there is a real guru in the room about Cython in the room, because access to memory view is always yellow.
Oh,
Because it double checks if it's not out of bounds, something like that.
you can switch that off.
Or if the pointer is not null. Well, it does an extra check
Mm.
somewhere when you're using memory views. Well, when you're using NumPy arrays, it doesn't check.
Okay. Yeah, maybe we can ask a Cython expert to discuss it afterwards. I don't know anything about that. All right. So, but that's how you access a basic NumPy array. Let me see if I've got that code written down for you. There's NumPy basic. NumPy basic dot. Okay, there's exactly that. So let's try and compile it quickly. What was it called? Foo. And oh, it takes an array as input. So let's make a zeros 5 by 5, and it must be of data type double. Oh, I guess it is already double if it comes out of zeros. Okay, so NumPy basic.foo of x. Yeah. So with the 5 by 5 input, why would I have done that? Shouldn't I just have filled up the array with? Let's modify that a little bit. Makes no sense to create a new output array here, does it? Just do it in place. So we're going to take the existing array value and just add 10 to it.
Return R, not out.
Thank you. There we go. Just notice there's, do I use CNP in here? No, I don't. Okay. Okay, so there you go. Does anyone have a European adapter from American? Otherwise, I have 15 minutes, so it's not a terrible rush. All right. Ah, perfect. Thank you so much. Right, so you were asking earlier on about the other array for defining Numpy arrays. And there it is. So this is the other syntax you may encounter out in the wild. You can do a C import of NumPy that imports the NumPy headers into Cython, and then you can use cnp.nd array and specify the data type and the dimensions. Yes, I'm good. Thanks. Right, so the next example, yes?
Is there a difference between C import and import of NumPy?
Yeah, so C import gives you access to the NumPy header, and import is basically an import of the NumPy library as you would have in usual Python. So, yeah. All right, so the next example is of matrix multiplication. So you're all aware of how matrix multiplication works. You've got a matrix A that you want to multiply with a matrix B. So how do you find, for example, well, this output element, you multiply this row by that column. So you'll have A11 multiplied by B12, A12 multiplied by B22, add the sum together and put it over there. So always the corresponding row and the corresponding column. Do the inner product of those. And here that's written out as a for loop. So first few lines just to figure out the shapes of the two matrices we're dealing with. So get the rows of A, columns of A, same for B. Then we create an output array using np.zeros of the appropriate number of rows of A and columns of B. And then we have a for loop that runs over the rows in A and over the columns of B. So that's over all our output elements. And then for K, in the number of columns in A, we do the pointwise element, the pointwise multiplication, and that we store in a variable S. So S becomes whatever its current value is, the corresponding value of A multiplied by the corresponding value of B. So that would be this, that times that plus that times that. Okay, so that's written out there. And then the output ij just gets assigned to the value of the sum. I can't actually, I guess I can show this for you on very small matrices, but it's not even worth benchmarking this because it's incredibly slow. So how would we improve the situation in Cython? Well, again, we can annotate the involved type. So we can say that the input matrix A is going to be a two-dimensional array of type double, the input B same, and the same for the output. Then we define rows, columns as integers, or the Python size type. Python size type also for I, j, and k. Again, it's just an integer. And then the sum is stored as a double. And the same code for the rest. We didn't modify anything else. Right, so all right, so there I've got that code. It's exactly the code that you just saw on the slide. So it's just been annotated with types. I also added 2 extra lines there at the top. Do you see the decorator Cython.boundsCheck and Cython.wraparound? So that makes working with arrays a little bit faster. It says that don't check when I try and index into an array. Don't check whether I'm outside or inside of the array. Assume the user is doing something responsible. And also don't enable wraparound. So if I use -1, don't refer to the last element because that also takes extra computation. So just do a straightforward indexing. Now, what I'd like to show you here is that it is very easy to parallelize code using Cython. And the only thing that I need to add, well, these 2 things. So from Cython, I import parallel range, and I just tell it that this snippet of code can execute without Python's GIL. And that you can only do if you're not messing with Python objects inside, but I'm not. I'm just messing with values in memory. And then you simply replace your range with a p range, parallel range, and then Cython will automatically split it for you into 2 simultaneously executing statements. So let's see how these fare. So there's the code I'm going to run. I'm going to generate matrices of dimensions 500 by 250 and 250 by 500. I'm going to fill those with random numbers, then multiply them together, store them in an output array. And just to check, I also multiply them with np.dot, and I compare the results. And I'm going to do the parallel version, and I'm going to do the normal version and the parallel version and see what the timings look like. The number one won't run because I don't have number installed, so I'd better take that out. All right. Okay, so there we have our results. For the standard Cython dot, it was 122.3 milliseconds. For the Cython dot with the p range, it's approximately half the time. There's a little bit of overhead, but it's roughly right. And numpy.dot took 17.1 milliseconds. So here's an example of what you said earlier on, is that, yes, it's not always a good idea to Cythonize. The Atlas guys know what they're doing. The Accelerate guys know what they're doing. MKL, whatever is underneath the hood in your linear algebra system is probably much better than you can do by yourself. Now, maybe if you're careful with the cache and you do things in the correct order and so forth, you can do a smidgen better than this, but I highly doubt that it's worth the effort if you can get that from using straightforward NumPy.
Is it with this Markdown library?
No, this is just there's just Atlas on my computer. Yeah, and I don't think it's even optimized for this machine specifically. So I'm not going to talk about wrapping Fortran today, but you can also wrap Fortran. So I've just pointed you there to Andrei Chertik's excellent notes. So feel free to have a look at that. Right, so this is how you wrap the simplest of C code in Cython. You'll see there I say cdefine from external math.h. So in other words, just import from math.h the following definitions, cos, sine, and tan. Both take a double, x as input, return a double as output, and I define a constant mpi as well from that header. So those are just definitions copied from that h header right in there, and then Cython allows you to use them in your code. So I can do cos of some number or cos of pi, and it will work. Yep.
The definitions are exactly the same, no underscores or extra stuff. In the header file, in the math header file.
Yeah.
The definition of those functions are exactly the same.
I think so. I mean, we can have a look. It's not, it's a, yeah, that's a complex file, but if you do man, would it be, there we go. So I just got it from the man file there. So. Anthony Scopads has got a project called Crossdress, I think, that also automatically generates these wrappers for you, so you don't have to do everything by hand. And you'll X is cross, right? Yeah.
But math is completely wrapped within Cython
It is?
from libc.math.
Oh, yeah, yeah, probably. There's just an illustration of how to do it, yeah. I mean, usually you'll put your own C code in there. The only change you need to make to your compilation or to your setup file is just you need to tell it to also link against libm, otherwise it won't have access to the function that was just wrapped. Here's an example of how to wrap C++. So we've got a namespace geometry. Inside that namespace, we've got a circle class defined. It's got several public methods, a constructor, destructor, several gets, several sets. Just ways of setting the circle and the radius, the center and the radius of the circle, and then these private members, the center coordinates as well as the radius. So that's my C++ header file. And correspondingly in Cython, I would say again, cdefine from this external file circle.h, pull it in from the namespace geometry, and then create this class cdef cpp class. So that creates a new C++ class called circle. And I wrap the constructor, the gets, and the sets with their appropriate input and return types. So again, just copied there from the header. And you have to do a tiny bit more work, and this is why Anthony's project is useful, because you have to do a little bit more work to access that C++ object. What I've done here is I've created an object called, a Python class called PyCircle, and the first member of that class is a pointer. It's called this pointer, and it's just a pointer to a C++ object, in this case to a circle object. And you'll see that I've got a special method there called _cinit, and that is the one which is going to construct the circle class. So cinit is the C initializer. So I say self.thisPointer is equal to new circle. So it instantiates a new circle object with the x, y, and r parameters provided. And now you've got a pointer to your actual C++ object. So now you can do whatever you'd like with that object. In this case, I define the deallocator. I say when this object is deallocated by Python, then also delete the pointer or delete that object, the C++ object. And for the rest, I just have proxies into the C++ object. So if I want to get the area, I call self.thisPointer.getArea. If I want to get the radius, I can get self.thisPointer.getRadius. So I'm creating a Pythonic interface on top of my C++ object. And again, you have to modify your build file slightly, but in this case, you just have to tell it to include the C++ header, your Python file, and then warn it that the language is C++. Right, so what we've seen here is that you can profile your Python code. Where it's slow, you can replace only the parts that you're interested in with fast optimized C code, all the while still coding Python. So high-level code with low-level performance. It's not a silver bullet, but I think it's a pretty good solution. Right, so that's it.
Is that picture symbolic?
Yeah, maybe the picture is symbolic.
Sorry, I missed. What was it? M? The library is equal to M? Like, what was the meaning of the M?
So that means that when you the question was, why is there libraries equal to M over there? It's because when you want to use cosine in C, you have to link against libm. So this just tells Cython to link against libm to get access to those math functions. If it was your own library, you would just put the name of your C library in there. There was another question. Yes?
What happens if your C++ code employs kind of threading POSIX threads either by OpenMP or by another library?
Yeah. So unless they manipulate Python objects, I guess that's fine. You're just not allowed to mess with Python objects because Python goes under the assumption that only one, only one thing is accessing each object at a specific instance in time. Does anyone else here have experience with using C-level threads in Cython? Okay, sorry. Yeah. Yep. Oh, you do? Okay, but do you have a different answer for him? Or?
No, I mean, there is no, basically, when you are getting in these threads, as you say, you just have to be careful not to mess with the Python line, but otherwise you can do whatever you want. I mean, I even, at some point, wrote CUDA code, and then used Cython to grab this, link to this library, and import it as a Python extension. This was easier than using PyCUDA and other things. And no problems whatsoever.
Cool.
And is there any support for, let's say, linear algebra within Cython?
I don't think Cython itself has got linear algebra support. No.
So this was a terrible mistake that you call, for example, this is inner dot product of the columns and the row of the two matrices.
Yeah, you would not.
I would move back to the Python space.
Yeah, absolutely. I would use Atlas to do that for me. Yeah, or numpy dot. Yeah. Yeah.
Can you debug a PyX file?
You can. I guess you could use your. Can you use your standard GDB tools for that? David says the answer is yes, but you don't really want to. I don't know. So what do you want to do?
I mean, because if you have to debug the silent code, it's very unavailable.
All right, but I guess the point is that you don't. If Cython is doing the right thing, then you won't be getting seg faults, right? Yeah.
To respond to that,
Yep.
I've had pretty good results using GDB, with GDB 7.4 or something with all the Python extensions and using GDB to debug both at the Cython level and in certain cases dropping below to debug the actual generated C code as well. The Cython extensions for GDB work really well.
Okay, so GDB with is it the Python extensions or the Cython extensions?
There's a Python extension for it for Cython debugging.
Oh, fantastic. Okay, so there is a Python Cython extension for GDB 7 that you can use, and according to Simon, works really well. Can I give you a slightly different demo on an entirely different topic, just because it's something cute that I ran across last week? If you will indulge me for 3 more minutes. So I was teaching at a radar company, and they asked me to show how you can do real-time plotting. And I came across a demo that Bryce Hendricks gave at SciPy recently on how to use Bokeh, which is his plotting package, to do real-time plotting. And I thought it was quite cute. So all right, here we go. That's the one. Okay, so I'm starting a server, and all this server is doing, it's basically monitoring the sound card, and it's serving on it's a Flask server. I can show you the source code. It's very simple, and it's serving on port 5000 of localhost. If you navigate to that port, that's not what I wanted to see. What's that? Ah, localhost, yeah. Localhost, there's the demo. What I wanted to show you was actually the data. So that's what the data looks like. And if you reload it, you just get new samples from the sound card. And there's the live plotting demo. So I can set the gain up a little bit, not too much. And then can stretch the frequency range a bit, and let's see. Maybe it's a bit lower. Ah, was it that at the bottom? Let's try again. No, that line seems to be there all the time. I'm not sure where I'm generating the note.
Yeah, is the X unit hertz?
Can you see it?
No, I mean the X is it hertz?
Ah,
It goes to like.
no, X is time, and I don't know what Y is. Oh,
Frequency value. Hertz is too high. Like you cannot go to 5K with human voice.
Yeah. I mean, most of the human noise is between.
no, but X is just oh, Y, yeah.
Yeah, why our X is You have left the frequency range, just remove it a little bit.
Ah, I see what you're saying. You're saying I should. Okay.
Oh, that looks right.
Nope. My microphone seems to do something. Anyway, so I thought that was a cute demo. And then, of course, as it happens, one of the participants of the workshop said, but it would be kind of cool if you could hook into the same data source using matplotlib. Won't you quickly write that up for us? Okay. So I set up. Let me see if I can find that. Yeah, so I set up this little guy over here. There we go. So there's this matplotlib script then hooks onto the same data server, and it polls the data server for data. And as soon as the data server has got protection in it, so you can't denial of service it, so it waits a little bit before it sends out new data. But as soon as it can get it, it's displayed in matplotlib. And I just wanted to show you how simple that is. So that's the code, 2 pages of code. so Matplotlib has got this animation module, and all I'm doing basically is I've got this class that, well, it initializes the plot. So these first lines just for initializing the plot. And then it's got these two methods. One is called update and one is called measure. The update frames per second is just so I can measure how quickly it's updating. But these are essentially the two methods that do any work. And you can see what it does is it basically takes the input data and it plots it. And that's it. And then over here is a measurement, and that's the important one. That's the one that connects to the server. So it takes URL-lib2, it connects to the server, it downloads the data as JSON. If there was any data returned, then just turn it into a Numpy array and yield that. So then the last important call is the one to matplotlib so from matplotlib's function animation, in the animation module, there's this function animation, and we pass as input the figure onto which we want to plot, the update function to call, the measurement function to call, and the interval, so how long it has to wait before it accesses those two functions. I set blitting to true. Those of you into graphics would know what that means, and then, yeah, just tell it which function to use to initialize the whole thing. So yeah, I just thought that was cute. Yeah.
Can you do that with images, and how fast can you do it?
Yeah, you can do it with images. In fact, here's an example of that. So this is just a function animation that, can you see the blocks color is changing? Yeah, so it's just generating images that vary in level between 0 and 1 over time, and then starts again from 0. So as it's doing this, I'm busy measuring the frames per second, and when I close it, it should print to screen. So yeah, 30 frames per second, and I'm plotting what size images. These are 255 by 255 images. So what size images do you have in mind? Probably very, very large images.
Well, few megapixels.
Yeah, no, we're not going to be able to do a few.
2048 by 2048.
Oh, that's very big. I don't think, but we can try, but I think it's going to be pretty darn slow.
Of floats.
Of floats. Oy. I'm sure it's not very happy right now. Did I? Did I make Vmax 0? That's not a good idea. Okay, so 2 frames per second. So for this purpose, you may want to approach matters a bit differently. Oh, but okay, there is one catch. I think yeah, so 2 frames per second, not very good. I didn't, there is a faster way to do it. Let me just see. Oh no, I'm using set data. Yeah. Yeah, so probably not for your application then.
Great.
I'm sure there are solutions, but I'll have to think a bit harder about it. Right, any other questions about Cython or life?
Just a quick one.
Yeah.
Does it make a difference if you use C import NumPy or if you import NumPy?
Yes. So C import NumPy in Cython gives you access to the headers, but you can't call the
So no, I mean, does it make a big performance difference?
no. So what I'm saying is they're for different purposes. The one gives you access to the C header. The one gives you access to the actual Python side of things. So import NumPy just gives you the normal Python access to NumPy. C import NumPy gives you access to the NumPy headers. So it's C specific, and it's just for if you want to have, for example, access to the definition of the floating point type or things like that. But I think you'll probably never need to do C import, so you can, not for most purposes anyway. Yeah.
Maybe one remark. There's this meeting between the decorator.
Yeah.
To specify the type, which is very nice. So you can have
Yeah.
pure hexagonal pricing to the decorator.
Mm.
And then if you want, you can provide all the types, all the local variables. So you see that you don't even see that inside anymore.
Yeah.
It's very nice because you can, if you don't have Cython stored, you can use your Python or you can compile it. It's the same kind of single source for two different purposes.
Yeah, let me see if I've got some of that. Yeah. I don't have an example here right now, but what he's saying is that you can, there's a decorator syntax as well that you can use to specify the types, and you can specify the types entirely outside of your function. So that means that if you run the source code through standard Python, it will still execute, albeit slowly. And then if you send it through Cython, it will compile it for you and make use of that type annotation. I'm not sure what the status is of type annotation in Python 3. I know there's some syntax included for it. I know there are discussions about it right now on the mailing list, but I don't know is Cython able to use those new type annotations? Does anyone know? Yeah, but that might be a new space that they'll explore soon, because the language does now support type annotation. And then you'll definitely be able to run your code in pure Python without any problem. All right, yep.
Can you specify the compiler, which one is used, or just like options for the compiler?
Yeah, so I think, David, how would you do that? Specify the Cython compiler? I guess it just, yeah. So it's currently, it uses GCC on my system, but how would you let it use Clang or? You can build it manually, sure, but the setup.py, oh, you know. Yeah, sorry.
When you do setup.py,
Yeah.
you can specify the compiler.
Okay.
For Windows, it's very common. And then inside your setup.py, you have to ask, you have to create build objects or something like that to define a class that will inspect which compiler is used. And for example, for the OpenMP extension, -f OpenMP becomes /OpenMP when you're using Microsoft Visual C++. And you can then adapt options for every kind of compiler.
Okay, so
But
it's doable.
It's
Yeah.
doable.
Okay.
Yeah, actually, I misunderstood the question that you need to setup.py with a --compiler.
-- compiler when you call setup.py.
Build one with big X. That's
Okay.
Windows, you choose between main window and
Okay. All right, so unless you guys have any further questions, then yeah, then I'm done. Thanks very much for your attention.